Okay, so let's take a look now that we understand what the atom looks like, we understand the experiments they did, the postulates, and how we kind of got here, what an element is. Let's take a look at the idea of atomic number and atomic mass. So before we continue on to all of this, so the periodic table is broken up into metals on one side and nonmetals on the other. So on the left-hand side, remember, these are all metals, these are nonmetals up in this corner. Again, the little thing right there, there's a little ladder right there. So sodium is a metal, and that's what it looks like. It very much looks like a metal. Copper, very shiny, very malleable. We use it for all sorts of conductive things. Here's bismuth, which is a little bit closer to that ladder. It's a little funky looking, and that's what we've got. Carbon, notice it's very brittle because it's a non-metal. And iodine. Iodine is actually this purple solid that gives off, it's really iodine comes as solid, but it comes as it turns into a vapor pretty quickly as well. So a lot of those things are vapor. So atomic number, the atomic number Z is, first of all, the number of protons in the nucleus. And most importantly, is it defines the element. Okay, so we don't have numbers on this one, but we will, I believe, on the next couple. So hydrogen, again, so this is, we focus on hydrogen. Hydrogen has an atomic number of 1, and the atomic number usually goes in the lower left. All hydrogen will have 1 proton. Lithium has an atomic number of 3. All lithiums are going to have 3 protons. If I add a 4th proton, it becomes beryllium. Okay, so the number of protons in the nucleus defines the element. So carbon will always have 6 protons. Beryllium will always have 4, hydrogen always have 1, so on and so forth. So the atomic number is always going to define the element. Those two things are always attached. Okay, so carbon has 6. Those two things are always going to be the same. I can always tell you, if I told you 6 protons, you would tell me carbon. If I said carbon, you would say 6 protons back, or atomic number of 6. Those things are eternally linked. Okay, so in the nucleus, we have, so this is what our basic atom is going to look like. This is way out of scale, by the way. The nucleus is tiny, tiny, tiny. So if we are taking everything on face value, so here's my nucleus. I have 3 protons. Okay, so 3 protons is going to make that lithium. So 3 protons is going to define that as lithium, lithium metal. Okay. We also have other parts of the nucleus, which are neutrons. I have 4 neutrons. Oops. Those neutrons are, these two things together is the total mass of the element, or it is the atomic mass. So the atomic mass is the number of protons plus number of neutrons equals the mass number. Okay, so the total mass number is protons plus neutrons. Those two things together make up the atomic mass of the nucleus, because electrons basically weigh nothing. Everything in the nucleus is the entire weight of the element. Okay, so this is where all of the mass comes from. Okay, the electrons are like 1/1000th of a proton or something like that. So it's very tiny in comparison. Okay, so we have 2 things. So we have atomic number, which tells you that defines the element, and we have mass number, which defines the protons and neutrons in the nucleus. So protons and neutrons in the nucleus, protons and neutrons in the nucleus. It is the mass of the number. Okay, so so just a couple of things. So a proton is typically, there's a couple of ways that we abbreviate it. weirdly, if we write H plus, that's like saying a proton, but you might see something like P1, okay, 0, that's another way of saying it, or just P for proton. The relative charge, all protons have a +1 charge, okay? And the relative mass is, let's just call it 1. Neutrons, so N, and we're going to say 0 and 1, or just N. Neutrons have a 0 charge. They only bring mass, which is 1. Okay, so again, a proton has this positive charge, and it has a mass of 1. And a neutron has 0 charge, but it also brings a mass of 1. An electron, I'm just going to do an E-, has a relative charge of -1, but it actually has no mass in compared to the other parts. So an electron is just like this little dot, and it has a negative charge. Okay, so just to give you an idea of the size comparison of those two things. Okay, so what we end up with is all of the protons in the nucleus. So if I have 3 protons in the nucleus, and I have a couple of electrons around the outside, I have 2 electrons around the outside, right? So I have 3+ from the nucleus, I have 2- from the outside, and we're going to get an overall charge, which is going to be the combination of those two. The overall charge is +1. I've got 1 extra proton than electron. We're going to do a bunch of examples with this in class. So the atomic mass number, we're going to use this term AMU, which is going to be the relative mass, are these atomic mass units. Atomic mass units. So 1 proton counts as 1 AMU. 1 neutron counts as 1 AMU. It's just, we don't have to worry about what it means. It basically just means 1 basic unit of charge, or 1 basic unit of mass for the elements, okay? We typically set up our elements or isotopes, we're going to talk about what isotopes are in a second, to look like this. The X is defining the element symbol. The Z is the atomic number. Again, the atomic number is the number of protons. And those two things are linked. The element symbol and the atomic number always have to line up. If I say it's carbon, it's got atomic number of 6. If it's 6, it has an element symbol of carbon. So those two things are always going to be lined up together. A is going to be our mass number. And the mass number is going to be protons, the total number of protons, plus total number of neutrons. Okay, good. So isotopes. Isotopes are anything, the atoms that share the same number of protons, but they have different masses. So if we take a look at something like carbon 12. So carbon 12, carbon also comes as what we call carbon 13. So carbon 13 has a different number. So look at for something to be an isotope, they have different masses, but they have the same atomic number. Essentially, it's the same element, different masses. Same element, different masses. And that's what we're looking at. And we'll get into defining these things. So there's a couple of ways that I can express this. I could say 13C, that's carbon 13. Or I could say carbon 13. Or I could say C13. All of those things are ways of expressing the elemental symbols or isotope symbols, right? It's me saying this is carbon with an atomic mass of 13. Okay. The last little bit is the thing that I didn't define yet. Up here in this corner, we are going to have the charge. Charge is going to be listed as the number of protons minus the number of electrons. And that whole thing is going to give us charge. Okay, so again, if I have a mass with 3 protons and 4 electrons. So I have 3 protons minus the 4 electrons, because electrons are negatively charged, the total charge is going to be -1. So this whole thing is going to have a -1 charge. Sorry about that. Okay. The other way to think about it is if I have 3 positives and I have 4 negatives, the sum of those is going to be -1, right? So we would essentially see those 3 cancel each other out and would have 1 electron left over. And that's kind of how we determine charge. And we're going to take a look at a bunch of these and we're going to be able to sort through this. Okay. So number of electrons in a neutral atom, number of electrons in a neutral atom. And so if it is neutral, they're going to have an equal number. So if I have carbon, we know that carbon has 6. Well, let's actually just take a look at carbon 13. So if we were to look at carbon 13, so how many protons does carbon 13 have? Carbon 13 has, well, again, it's defined by the atomic number. So 6 protons. No, I need to write that, 6 protons. How many neutrons does it have? Again, the neutrons are the 13. That's the mass number. Remember, that's both. So 13 minus the 6 gives me 7. So we're going to end up with 7 neutrons. Those two things together should give you the mass number back. And it does, which is 13, right? And then electrons. Okay, so if this is neutral, if there is no charge up here indicated, the number of protons equals the number of electrons. Again, if it is neutral, they are equal. Okay, they're equal at a neutral charge. So number of positive charges equal the number of negative charges. Okay, so we have a couple of examples here. So let's take a look at how many protons, neutrons, and electrons are in iron 55. Okay, so how many protons, how many neutrons, and how many electrons are in iron 55? Okay, so I'll let you take a moment and look at this iron compound, pause this and figure it out. So you're right that it has 26 protons because the atomic number is 26. There are 26 protons. Because it's neutral, again, we don't see a charge in this upper right-hand corner. The number of protons equals the number of electrons at 26. And finally, the difference between those two, 55 minus 26 is, what are we at? 24 plus, so 29, right? So 29 neutrons. And again, those things should add up to give me, 55. So 55. So again, those two things have to add up to give me 55. No charge in the corner, meaning the protons and electrons have to be the same thing. Okay. So with that said, how many protons, neutrons, and electrons are in lead 207? What is the symbol? Can you write out the symbol for something with 39 protons and 50 neutrons? And we're going to do a handful of these in class as well, but this is a good start. Okay. So if you look at the periodic table, and I think we're probably going to end up doing this in class. We will do these problems in class, but we're going to talk about one last little bit, which is called mass spectroscopy, or really what this is called is natural abundance. In nature, this is, well, first of all, this is magnesium. And the magnesium at the microscopic level is made up of a bunch of different atoms of magnesium. But magnesium actually has notice this dark one here, that's magnesium 26. Most of them are these light ones, which are magnesium 24, but there are some less light ones that are magnesium 25. Basically, if you look at the periodic table, you're going to notice that mass numbers are not precise. They're not like 24 or 25 or 26. It's some combination of these different things. So if I were to take any sample of magnesium anywhere on Earth, I would find out that it is made up of 79% magnesium 24, 10% magnesium 25, mass 25, and 11% magnesium 26. So we actually see this as there's a small percentage of all of these different isotopes in any magnesium sample that we have. So that atomic weight is actually the one that you see on the periodic table is actually a weighted average of those naturally occurring isotopes for an element. So we're going to have a simple equation for this, by the way. This is exactly how we calculate a grade, in fact. So why does magnesium have a mass of 24.305 on the periodic table? And it does. So if we go down to our periodic table and we zoom into magnesium, we see that it's 24.31. In fact, this is cut off even more, but 24.305. Okay. So the question is, why is that true? Why do we have to have that weird number of 24.305 in the periodic table? So we're going to do a quick calculation. So first of all, I'm going to just make a quick table here. I'm going to have abundance, or really what that is percentage, okay, in just decimal form. And we're going to have the mass, and the mass is going to be in AMU, okay? So the abundance of magnesium is 0.79, okay? Or again, this is just percentage in decimal form. Okay, so percentage, I should say, to a number, I guess. So that 70, it has an abundance of 79% or 0.79. Okay, and that one is magnesium 24. So the one with magnesium 24 has a mass of the isotope Mg24 has an abundance of 79%. The abundance of magnesium 25 has a 10% abundance and an 11% abundance for magnesium 26. Okay, so those two things, there we go. So what I want to know is, what is the weighted average? Any piece of magnesium that has 79% magnesium 24 is going to kind of give me a weight closer to 24, but it also has a couple of heavier things. So we know it's going to be above. It's not 100% magnesium 24, right? So what that means is any magnesium piece is going to have some average of all of those, which we have here. So how we calculate this, again, this is called a weighted average. This is how you would do an exam. Like our exams are worth 20%. Each exam kind of goes in this category and gets weighted this kind of way. So in order to do a weighted average, I'm going to take the abundance times the mass of each isotope, and I'm just going to keep doing that. Okay, so this is how it's going to go. I'm going to take the abundance of 0.79% or set 0.79 times the mass of 24 AMU. Plus, I'm going to do the 10% that is coming from 25 atomic mass units. Plus, I'm going to do the 11% from 26 atomic mass units. So when I do this math, okay, so when we do this math, we figure out exactly what we've got. So all right, let's take a look. So 0.79 times 24 gives me 18.96 AMU. 0.10 times 25 gives me 2.5 AMU. And then 26 times 0.11 gives me 2.86, okay, AMU. So when I add all of these up, so 2.86 plus 2.5 plus 18.96 gives me 24.32 AMU. So right there, we have the atomic mass that we find on the periodic table. Okay, so that's essentially what we're going to look at. That's what we're going to work out in class. What is the atomic weight? What is the anticipated atomic weight of carbon if we have this? And when you calculate this, it should be the same on the periodic table. Same question here. What is the atomic weight of neon? Again, it should be the same thing that you see on the periodic table for neon. And which one of these is the most naturally occurring? Well, we look at the mass of silicon, we should be able to figure that out. So we're going to do all of these in class next time. But yeah, that should cover all of the content for chapter 4.